everyone. Welcome to OneClass. My name is Shanjida. I am currently a second year human biology student at U of T. So today I'll be going over some commonly asked chemistry questions, both at the high school and college/university levels. And if anyone needs any additional help with schoolwork or needs tutoring, please check the description box. And other than that, let's get started. Okay, so our first question here says, how is the enthalpy of fusion calculated? So how is the enthalpy of fusion calculated? Okay, so basically the enthalpy of fusion of a substance is also known as heat of fusion. And so what this is basically the change in enthalpy resulting from providing energy. So basically you're giving energy to the substance, and it's typically heat, providing heat. It's a source of energy, okay, to a substance. And so basically what this means, like if you provide heat to a particular substance, in this case it would be a solid, right? A solid. So you provide heat to a solid, which will ultimately become a liquid. And so this state of change is due to the change in enthalpy, heat of fusion. And so this is basically what enthalpy of fusion is. Basically you're going from a solid to a liquid by providing heat. And so how to calculate it? It's basically, you have this formula where this is delta HF for fusion, basically. And you can basically have, so the delta HF, basically the delta means change in enthalpy, right? So you're changing states, for example, and to find this you have LF over N, where N is the number of moles, and LF is found from, so LF is found from your it's found from this equation, which is basically Q. So basically LF, you'll find LF from this equation is Q minus Q of solid. So this is minus Q of liquid. Okay, and where Q is basically, Q is delta Q, so this whole thing here is delta Q over here, and this is delta Q, and this would be the result. And so delta Q is C, so your specific heat capacity times M times change in temperature. Okay, so this is, the LF is latent fusion of heat of fusion. And so this is how you calculate the heat or the enthalpy of heat of fusion with this equation. And N is the number of moles. And so here they have given an example where if we have basically, so the units for this case would, so the units of heat of fusion is kilojoules per mole. Okay, and so basically over here they have an example where when 1 mole of ice, for example, is melted, we find from an experiment that 6.01 kg are needed, right? So this is basically an simple example. So in this case, the enthalpy of fusion of ice would be, so we have 1 mole of ice, right? And they said that the energy needed is 6.01 kilojoules. So basically we can just plug this into the equation where HF, delta HF is basically, right, you have 6.01 kilojoules, and so you have 1 mole, right? And so basically this would be 6.01 kilojoules over moles. So this is basically what enthalpy of fusion is. And so this is, yes, this is correct. Okay, what are, our second question here says, what are chemical formulas? Okay, so chemical formula is a way of presenting basically information about chemical proportions of atoms that constitute a particular chemical element symbol. So for example, so basically a chemical formula is where you have a balanced equation. So for example, if I say it's basically it comes from a balanced equation. So for example, here it says we have given a chemical formula of carbon monoxide, basically, so CO. This is basically a chemical formula. So it makes up a compound, basically. It's in a balanced form, makes up a chemical, it makes up a chemical element, basically. And so over here you can see there's 1 mole of carbon and 1 mole, sorry, not 1 mole, there's 1 atom and 1 atom of oxygen, basically. So when you're writing a chemical formula, it must be in a balanced, it must be balanced, basically. So it has to be in a balanced state. That's how it gets its name, basically. So if I, for example, if I had CO2, right, this is basically carbon dioxide, right? And so yes, so basically a chemical formula represents an element or compound in balanced equations. So the ratio over here, they're saying that CO is 1:1. So basically for every carbon atom there's 1, this is supposed to be 1 oxygen atom. So we also know that it has no charge. So basically, yes, a chemical formula does not have, so it has neutral charge, so a charge of 0, right? Of 0, basically. So yes, this is correct. Okay, so our third question says, what is the molar mass of nitrogen? So what is the molar mass of N? So N is, if you know what N is nitrogen. And so to find the molar mass mass is basically equal. It's basically the same thing as, I won't say equal, so is the same thing as the atomic mass of an element. Okay, so for example, if you recall that an atomic mass, how you find the atomic mass is by counting the number of protons plus the number of neutrons, which equals to your atomic mass. And so in this case, to find the molar mass of nitrogen, you basically need a periodic table. And so basically the atomic mass is equal to the molar mass, is the same thing. So if you look in the periodic table, it's basically given where 1 mole of nitrogen is basically, you just add up the two numbers, right, the protons and the neutrons. So the atomic mass of nitrogen, so you can probably basically, so the atomic number, if we just do this, atomic mass, right, of nitrogen is equal to, so basically it has, if you look in your periodic table, it has 7 protons and 7 neutrons. Okay, so basically it has an atomic mass of 14 AMU. This is also equal to the molar mass, so we can also say that the molar mass of nitrogen is also equal to, but the keep in mind the units change. So when we're talking about molar mass, it's grams per mole. Okay, so the molar mass of nitrogen is 14 grams per mole. And I would suggest using the exact values from the periodic table. Here I just rounded it, so basically the same thing. Okay, so fourth question here says, how is the molality of water calculated? Okay, so the molality of water is basically calculated, so the molality of, how is the okay, water calculated. So molality is is defined as the number of moles of a solute per kilogram of solvent. So molality is equal to basically the number of moles of solvent, of solute, right, over the, so per kilogram of solvent, so the kilogram of solvent. Okay, so we can imagine that the units for this would be moles per kilograms. Okay, so how to calculate water, the molality of water. Let's say we have 1 liters of water. Okay, so basically we need temperature also. So in this case, let's say at 25 degrees Celsius, the water has a density of 0.9970749 grams per milliliter. Okay, so we can say that the mass, therefore in this case the mass, right? So you get how you get mass is basically, you know, density is equal to mass over volume, and so therefore mass is equal to d times v, and so v in this case is 1 liters. So you just multiply density times 1, and so we just get 0.99707. I'm just leaving it like this, of grams. Okay, or I'll just write the whole thing. Okay, so mass is basically would equal to 0.9970749 grams. And so to calculate the number of moles, so if you recall from this that to calculate the number of moles, we have to calculate the number of moles, we are going to use this equation where we know that molar mass is equal to mass over moles, right? And so to calculate moles in this case, we would just say we rearrange this equation and we get mass over molar mass. And so what we need in this case is to find the molar mass of water. So the molar mass of water is, if you calculate this molar mass and break this, and first find the molar mass of hydrogen and then the molar mass of O2. So the molar mass of one hydrogen atom is around 0.11 grams per mole. Again, you get this from the periodic table, and this we have 2 atoms of O2, and so we get here around approximately 16.01, I guess, grams per mole. And so, oh sorry, never mind, it's H2O, my bad, H2O, and so this is going to be 2.01 grams per mole. And so the molar mass of oxygen, one oxygen atom is 16.01 kilograms per mole. And so if you add this together, you get molar mass of H2O is basically around 18.02 grams per mole. Okay, and so over here, if we have our mass and our molar mass, so we can calculate the number of moles, which would be 0. And so if we convert this, sorry, this is kilograms. And so if we want to convert this into grams, right, because we're dealing with grams per mole, and so we need to convert this into grams. So let's first convert 0.9970749 kilograms to kg, 2 grams, sorry, we would have to multiply this by 1,000 since 1,000 grams equal to 1 kg. And so what we are going to do is multiply this with that by 1,000, and what we get is, and so 0.9970749 kilograms is equal to 997.0749 grams. Okay, and so then what we have our grams, we have our molar mass, and so now we can calculate the number of moles. 997.0749 grams over 18.02 grams per mole. And so you can cancel out the units here, grams and grams. So then what you have here is basically, if you divide these two, you would get 55.348 moles. So this is the number of moles of H2O. And so now we have our moles and we have our kilograms of water, we have the mass of water, and so now we're gonna calculate the molality. So you write molality, so the symbol for molality is a small m, basically. It's also a small m. Okay, and so to calculate molality here, we are just gonna use the moles of water, H2O, over kg H2O. And so what you have here is 55.348 over our grams, or our kilograms. Our mass was 0.9970749, right? And so basically the molality of water is approximately 55.510 molality. So the symbol for molality is a smaller case m. This is a smaller case m. Okay, and so this is the answer. And so yes, this is what they have got, and this is correct. Okay. Fifth question says, what is the molar mass of helium? Okay, so again, the molar mass of helium, you basically find the molar mass of, so I'm just gonna denote as mm as molar mass. And so the molar mass, to calculate the molar mass, is again the same thing as atomic mass. So if you say the atomic mass of helium, right, is the number of protons plus the number of neutrons, right? So you'll get this from your periodic table. The number of protons in helium is 2, and so the number of neutrons is also 2. Okay, and so the atomic mass is 4 ANU, and so we can say the same thing for the molar mass. And so the molar mass of helium is also around 4.0 grams per mole. So you just have to convert the units. 1 AMU is basically the same thing as 1 grams per mole, okay? And so this is the molar mass of helium. Yes, this is correct. Okay, so what is the molar mass of mercury oxide? Okay, so mercury, so this is mercury 2 oxide. So if you recall that mercury has a charge of +2, whereas oxygen has a charge of -2, right? And so when you're writing the chemical formula for this, you are gonna use, so mercury 2 has a charge of +2. So when you're writing a chemical formula, you know that you change the you basically reverse the charges. So what I mean by that is basically if you have, this is mercury and it has a charge of +2, oxygen has a power of 2 negative, right? And so when you're writing the chemical formula, this goes here, and then this goes here. So what I mean by that is you have Hg2 and you have O2, but since the subscripts are the same, you can basically write this as HgO, right? Because the ratio is 1:1, so it's HgO. And so now we're trying to find the molar mass of mercury. And so mercury has a molar mass. Molar mass of mercury is given in your periodic table. It's 201 grams per mole. And so the molar mass of oxygen is 16 grams per mole. And so to find the molar mass of mercury 2 oxide, you just have to add these two together. And what you get here is 217 grams per mole. And so this is right. This is correct. Okay, our 7th question says, how do you determine pH from pKa? Okay, so the pKa value, it could be used to measure the strength of an acid. When we're talking about pKa, right, we're talking about acids. Right, whereas pKb is for bases. And so how we can do this, so to find the pKa is the pH of a chemical species that will accept or donate a proton. Okay, so basically the lower pKa means the stronger the acid. Stronger acid, so it is able to donate a proton. So hence, so then stronger acid. Acids are readily able to donate their proton, which is H plus. Okay, and so for example, if we have an acid and we have to determine the pH, so what we can do is first write out the general equation in aqueous solution, and that is by writing it like this. HA in aqueous. So this is an equilibrium. This is an equilibrium equation, and so you just break the acid, and so when it dissolves in solution, it becomes an H plus an anion. Okay, and so to calculate the pH of this, you have basically, to calculate the pH, you do pH is basically the negative log of the concentration of your proton, so H plus. Okay, and to calculate pKa, so to calculate pH from pKa, so this is basically pH would equal to pKa plus log of the concentration of your anion. Sorry. Negative over your H, your proton. Okay, and so this is how you determine the pH from pKa, whereas you can also calculate the value of the acid dissociation constant, which is Ka. So acid dissociation constant is Ka. So to find Ka, we can also find this from knowing the pKa. So this is basically 10 to the power of negative pKa. Okay, and so for a strong acid, the pKa is greater than 1, and Ka is basically less than 1. Okay, so if you have a Ka of less than 1, it says means you have a really strong acid basically, and so this is the answer. And yes, so for strong acids, it means that your H is basically completely dissociated in the aqueous solution, and so basically your H concentration of your proton is equal to the concentration of your acid. Okay, because it's completely dissociated, and so the pH is basically You can also say pH is basically the negative log of your acid. Okay, and so this is also correct. This is correct. Okay, so our eighth question says, what is the Lewis structure of SF2? Okay, so a Lewis structure is a graphic representation of the electron distribution around the atoms of an element, of a compound. So it is an important tool basically to predict the number and type of bonds that can form around the atom. So it also helps to predict the geometry of the molecule as well. So the steps to do this, so we have SF2, and so to calculate the number, so what we're going to do here is calculate the total number of valence electrons. And so, we have sulfur here and we have fluorine. Okay, so the number of valence electrons of sulfur, of S is 6, right? And so the number valence electrons of fluorine, I have 2, basically we have 2 in this case. So one fluorine atom has 7 valence electrons. In this case we have 2, so it would be 2 times 7 and it will equal to 14. So if you add this together, the total number of valence electrons is 20. Okay, and so the next step, what we have to do is determine the number of electrons needed for bonding. So since there are two F atoms, the number of electrons needed for bonding is 4. Okay, so there's 2 F atoms, right, fluorine atoms, and so we would need 4 electrons to bond, like all together. And so then the next step would be to find, so this is the second step. The third step would be to determine the number of lone pair electrons. So the remaining electrons are used as lone pairs for central or terminal atoms to achieve an octet to finish the Lewis dot structure. So to calculate the electrons used as a lone pair would equal, basically, so we have 20, right, all together, and we need 4 more atoms to bond, so we do 20 minus 4 and we have 16, right? So the total number of lone pairs, so total number of lone pairs would be 8. Okay, so now we're going to draw the Lewis structure with the given information. And to draw this, so since we have 2 fluorine atoms, those are going to be the outside, whereas our central atom would be sulfur. Okay, so sulfur, as you recall, it has 6 valence electrons, so let me just, okay, and so So then we have 2 fluorine atoms. Okay. Let me draw this. Okay, fluorine. And so I'm just gonna erase these 2. Okay. And so it has another lone pair too. Oh, actually, I'll draw this later. And then, so fluorine has 7 lone pair, valence electrons. So 1, 2, 3, 4, 5, 6, 7. So it's bonding with the sulfur right here. And so this one also has 7, right? And so in this case we need 8. So now what's left, we need to add the lone pairs basically. And so you can see there's 1, 2, 3, 4, 6, 7. And so now we need 1 more pair and it would go to our sulfur. Okay. I'll just draw this lone pair over here. Okay, so you can see how we have 1, 2, 3, 4, 5, 6, 7, 8. 8 lone pairs. Okay, and so this is how you draw the Lewis structure of SF2. This is our pair. Okay. And so this is, yes, this is correct. Okay. Our next question says, what is the molar mass of sucrose? Okay. Sucrose. So sucrose is a glucose molecule. It's a type of glucose. And so to find the molar mass of sucrose, we need to know its chemical formula. And so the chemical formula of sucrose is C12H22O11. Okay, so it has 6 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. And so to find the molar mass, let's break the chemical formula into their atoms. And so molar mass, let's first find the molar mass of C12. Okay, and so the molar mass of one carbon atom is 12.01 grams per mole, and again you get this from your periodic table, right? So 12.01 grams per mole, and since we have 12, we just multiply this with 12 and you get 144.12 grams per mole. Okay, and so then the next step would be to calculate the molar mass of 22 hydrogen atoms. So the molar mass of one hydrogen atom is 1.01. And since we have 22, you have to multiply this by 22. And what you get is 22.22 grams per mole. And so the next step would be for us to find the molar mass of oxygen. So we have 11 atoms of oxygen, and so the molar mass of one oxygen atom is 16.16 0.0 grams per mole. And so we have 11 here. You multiply this by 11 and you get 176, right? Yes, so you get 176.0 grams per mole. And so to calculate the so you have to add this together, and you would get basically the molar mass of sucrose C12H22 H22O11 is basically, you have 144 point, it was 112 plus 22.22 plus 176.0, and so what you get here is basically this plus, so what you get here is basically 342.34 grams per mole. Okay, so this is the molar mass of sucrose. Okay, and this is right. Okay. Next question says molar mass of benzoic acid. Okay, so benzoic acid. By the name, you can probably guess it's an acid, and so the chemical formula of this is C7H6O2. Okay, and to calculate the molar mass, we need to know the chemical formula. This is one of the crucial things we need to know. And so to calculate the molar mass, let's break the chemical formula into three separate atoms, basically, or no, three separate units here. So for first, let's calculate the molar mass of carbon. So the molar mass, so we have 7 carbon atoms here, and so the molar mass of one carbon atom is 12.01 grams per mole. Since we have 7 in this case, we have to multiply this by 7, and so what we have here is 12 times 7. We have around 0.01 times, and so we have 84.07 grams per mole. And so the second step would be to calculate the number of the molar mass of 6 hydrogen atoms. And so the molar mass of H6, so the one mole or one atom, 1 mole of hydrogen is 0.11 grams per mole. And so since we have 6, we're going to multiply this by 6, and so what you have here is 6.06 grams per mole. And the third step would be to calculate the molar mass of 2 oxygen atoms, and so the molar mass of 1 oxygen atom is 16.0 grams per mole. And since we have 2 in this case, we'll multiply this by 2, and so what we have is 32.0 grams per mole. Now what we're going to do is basically add this all together. Molar mass C6H7 would be, so we would add this all together, so 84.07 plus 16.06 plus 32.0, right? We'll add this, and what we have here, sorry, 6. Okay, 6. Okay, plus 6.06 plus 32. And what we have here is 122.13 grams per mole. Okay, and so the molar mass of benzoic acid is 122.13 grams per mole. Yes, this is correct. Good job. Okay, so next question says, what is the molar mass of acetic acid? Okay, so also by the name you can probably guess that this is an acid. It has a proton, and so the molar mass of acetic acid, so the chemical formula of acetic acid is CH3COOH. Okay, so in this case I would calculate the carbon atoms first, the molar mass of the 2 carbon atoms here. And so the molar mass of, I'm just gonna write, since it's not C2, be 2 C's, it would be, so the molar mass of 1 carbon atom is 12.01 grams per mole. We have 2 in this case, times this by 2, and you get 24.2 grams per mole. Okay, and so the next step for me what I would do is find the molar mass of the hydrogen atoms in acetic acid. We have 4, and so the molar mass of 1 hydrogen atom is 1.01 grams per mole. We have 4 right here, so you multiply this by 4, and you get 4.04 grams per mole. And the second last step would be to calculate the molar mass of the two oxygen atoms, right? This is not printed, it's L, right? So it would be, so the molar mass of 1 oxygen atom is 16.0 grams. And we have here 2, so it would be 32.0 grams per mole. So now the last step would be to add all this together and to find molar mass of CH3COOH, which is acetic acid, and this is equal to, so our first one was 24.2 grams per mole plus 4.04 grams per mole plus 32 grams per mole. And so if you add all this together, 24.2 plus 4.04 plus 32, you would get 60.24 grams per mole. Okay. Yes. Yes, so yeah, this is what I've got. So this is your 0.2. Okay. And so in this case it would be 0.6. And so yes, this is correct. Okay, so our next question here says, what is asymmetric carbon? Okay, so an asymmetric carbon is also known as a chiral carbon. So asymmetric carbon is also known as a chiral carbon. And what a chiral carbon is, so if we have a compound here, a hydrocarbon base, or an organic compound carbon chain basically, so our central carbon here, so let's say this is our central carbon, it would have 4 distinct groups basically, any 4 distinct groups. So let's it would have different atoms basically. It could be double bonded, a carbon oxygen, or with, so it has to be basically 4 different bonds basically. And so we can have, for example, a hydroxyl group, an alcohol group, an amide, right? We can have fluorine here, or we can have, and lastly we can have a hydrogen. In most cases there will be an hydrogen with a chiral carbon, so, and then we have 3 other groups basically. But a chiral carbon has 4 distinct bonds basically, or it has 4 different groups. So it can't be the same, or else it won't be a chiral carbon. 4 different groups of compounds or atoms. Okay, and so this is what a chiral or an asymmetric carbon is. And so over here you can see they have 4 distinct groups of atoms or compounds, and so this is correct. And so if you liked today's Q&A and would like to get updated whenever we upload a new video, please subscribe to this channel. It's OneClass, and please like, share, and subscribe to this channel also. And also, if you really liked our videos, or really like our videos, share them with your family or friends. And if you guys have any personal questions, you can follow the links down below and ask them. And other than that, I'm Shanjida, and I'll hope to see you soon.